Hello class, this is Jared Cameron, an Associate Professor of Engineering Technology at Lone Star College Sci-Fair, and right now I'm going to do an example problem in which we are trying to find unknown forces on a system in equilibrium. Okay, so the first thing that I'm going to do is I'm going to draw my free body diagram. So I'm going to go over to the side. I'm going to draw a free body diagram based on this point at B. We already know from previous statics problems that the tension in this cable right here is just going to be the weight of this block, which is 15 kilopounds. So we have one force coming down at 15 kilopounds here. We also have a force pulling away here, and this is a cable, so we know that all cables are going to pull, and so we know the force is going in the upward right direction, and that is from B to C. I'm also going to draw a dotted line representing the horizontal here. We also have a force coming down this way, and that is segment AB, or cable AB, and that makes a 80-degree angle with the vertical. We also know that from the horizontal up here, this force or tension from B to C makes 75 degrees. So in doing my free body diagram, I label all of the forces, and I also want to go ahead and determine what their angles are with respect to the horizontal. Okay, and so I need to find out what this angle is. Now if we look here, we see that we have parallel lines, and these are interior angles, and so by the interior angle theorem, we know that these are the same value. You can also, if you want to, go ahead and make a 90-degree triangle, and knowing that here you have complementary angles, so they have to equal 90 degrees, so this would be 15 degrees. And then there you know that this is a triangle, and so it has to add up to 180 degrees. You have 90 degrees plus 15 degrees, then this will have to be your 75 degrees here. Also, you have another 90-degree triangle here, and knowing that this is 80 degrees and this is 90 degrees, then this has to be, this angle with the horizontal has to be 10 degrees to add up to 180 degrees. Okay, and so now we have our complete free body diagram. We have all the angles, we have all the forces. What we want to do now is we want to resolve these slanted forces into rectangular components. That means that each slanted force is going to have a force in the x component and then a y component that makes up the original force. Alright, and so I'm going to go ahead and label this tension as tension BC, and I'm going to go ahead and label this tension as tension AB, so that we have our values here. And these are the forces that we're trying to find, tension in BC and also the tension in AB. And so I'm going to break these up into rectangular components. That means I'm going to have a component of the force that goes this way, and then one that goes up this way. On the other side, for this slanted force, I'm going to have a force that goes this way and another one that goes down this way. So I have an x and a y component of each of my slanted forces. So this y component is just going to be the magnitude, which is TBC, and we're going to multiply by the sine because we are opposite of our reference angle. So the magnitude times the sine of 75 degrees is going to be the y component of TBC. The x component of TBC down here is going to be the magnitude, which is the tension in BC, times the cosine of our reference angle, which is 75 degrees. Our x component of our force or tension AB is going to be the magnitude, which is TAB, times the cosine of our reference angle, 10 degrees, and our vertical component or y component of the tension AB is going to be the magnitude tension AB times the sine of our reference angle, 10 degrees. Okay, and so now we have all of our forces. We have 1, 2, 3, 4, 5 forces. Remember, these slanted forces have been resolved into these rectangular components. So now what we need to do is develop our equilibrium equations, and that's to say that the sum of the forces in a particular direction is going to equal 0. All right? So we know the sum of the forces equals 0. We're going to assume that going to the right is positive. Right? So we'll need to add up, or we need to represent all of our horizontal forces in this equation. So our first horizontal force is the x component of the tension AB. And so we have TAB times the cosine of 10 degrees. Now, since that is going to the left and our convention says going to the right is positive, I'm going to subtract that particular force. Our other force in the x direction is the tension in cable BC times the cosine of 75 degrees. So I'm going to add that because it's going to the right. So we have the tension in cable BC times the cosine of 75 degrees. All right. Now, these are my only forces in the x direction, and so all of those are supposed to add up to equal to 0, which I've already said over there. Our next equation is going to be to sum the forces in the y direction. That's supposed to equal to 0. So what forces do we have in the y direction? Well, we have tension AB times the sine of 10 degrees. So tension AB times the sine of 10 degrees. And I'm also going to subtract that force because it's going down, and our convention is that going up it's positive. Next we have 15 kips, which is also going down, and so I'm going to subtract 15 kips. Our next vertical force is going to be the tension in BC times the sine of 75 degrees. That's going up, so I'm going to add that. So add the tension in BC times the sine of 75 degrees. Okay, and all of that is supposed to equal 0. So these are my two equilibrium equations. I have two equations and I have two unknowns. My unknowns are the tension in AB and the tension in BC. So I can solve this several different ways. I can do substitution. I could do Kramer's rule. I could even use the RREF function on my graphing calculator, reduced row echelon form. What I'm going to do for this particular video is I'm going to do substitution. So in substitution, your first step that you want to do is you want to take the easiest equation and solve for one variable. So I'm going to take our equation up here because it only has two terms, and I'm going to solve for one variable. That means I'm going to take tension in AB times cosine of 10, and I'm going to move it to the other side of the 0. And we're going to have tension in AB equals, tension in AB times the cosine of 10 degrees is going to equal tension in BC times the cosine of 75 degrees. Okay, so now I'm going to continue to solve this for a variable. It doesn't matter which one you solve for, so I'm just going to solve for the tension in BC. So that means I'm going to divide by the cosine of 75 degrees on both sides. These are going to cancel, and I get that the tension in BC is going to equal to the tension in AB times, and when I take the cosine of 10 degrees divided by the cosine of 75 degrees, I'm going to get 3.805. Okay, and so when I'm actually plugging in numbers to my analysis at this point, I'm going to take it to 4 significant digits because at the end my answer needs to be in 3 significant digits. All right, so that's very important. So now I have one variable solved for. Tension in AB, or tension in BC, equals the tension in AB times 3.805. So what I'm going to do from here is I'm going to take this value and I'm going to sub it into this equation. All right, and that equation says negative the tension in AB. So actually, to make this a little bit easier, I'm going to go ahead and start out with this second equation, and I'm going to move things around a little bit to make it easier for us to substitute in. So we start with negative tension AB times the sine of 10 minus 15 kips plus the tension in BC. Okay, and so what I'm going to do is I'm going to take the tension in BC times the sine of 75, right, minus the tension in AB times the sine of 10 degrees. Okay, and all that is going to equal my 15 kips. Okay, so you can see how I just moved things around just a little bit. Now I'm going to substitute in the tension in AB times 3.805 in for every place where I see the tension in BC, which is right here. Okay, and so instead of putting the tension in BC, I'm going to put the tension in AB times 3.805 0.05. Okay. Now I still have to multiply by the sine of 75, and then subtract by the tension in AB times the sine of 10, and now that's going to equal 15 kips. Okay. Now from here I can go ahead and multiply these two together. Okay. And when I multiply these two together, I get the tension in AB times 3.675. Now I still am subtracting the tension in AB here as well. I go ahead and calculate the sine of 10 degrees, and I'm going to get 0.1737, and that's supposed to equal 15 kips. So now you see I have two terms and they have the same variable, so I can combine these terms. So I'm really going to have the tension in AB, and I'm really taking 3.675 minus 1.737, and that's going to give me 3.501. And all that's supposed to equal 15 kips. I divide both sides by 3.501. And that gives me that the tension in cable AB is going to equal approximately 4.28 kips. Okay, and so I've of course rounded that to 3 significant digits as per what I normally do. So now what I'm going to do is I'm going to take this value. I'm going to take this value of the tension in AB, and I'm going to plug it into our equation right here to determine what T tension in BC is. Okay, so instead of putting the tension in AB, I'm going to put 4.28 kips. So we have 4.28 times 3.805 is now going to equal the tension in cable BC. And so when you calculate that out, you find that the tension in cable BC is going to equal 16.3 kips. Okay, so I have just worked out an equilibrium problem for you in which you have two unknown forces. We did the free body diagram. We found out all the angles with respect to the horizontal, and then we resolved the slanted forces into x and y components, and then we wrote our equilibrium equations in the x direction and also in the y direction to determine our equations. Remember, the sum of forces are set equal to 0 in the x and in the y directions. From there, we use substitution by taking the simplest equation and solving for one variable, and then substituting that back into our other equation right here, and then solving for the remaining variable, which was the tension in AB, equals 4.28 kips. Plug that back into our other equation, and we find out the tension in BC equals 16.3 kips. Thank you very much.